So, the first example that I have is the following. So, I am given the following plant condition. Let me say my plant condition is as follows. So, x 1 dot is equal to x 2 and x 2 dot, the dot represents the time derivative, is equal to x 1 is equal to u, u is a function of t, and my performance index is given by j is equal to integral t 0 to t f times half u square dt, and then we need to find the optimal control and the optimal state, right. So, basically we need to find u and x is a vector in this case. Notice that this is a case where the cost function is set equal to 0. So, we will follow the step by step procedure, namely the Pontryagin procedure. So, step 1 is we set up the Hamiltonian. So, my Hamiltonian H is V plus lambda times f, or this is also equal to half u square. So, that is my V plus lambda. So, now notice that we have a set of two equations in the plant condition. So, lambda takes a vector form. So, I get lambda 1 times x 2 plus lambda 2 times u, right, and then so then the step 2 is find u star. So, find u star, and we do that by differentiating h with respect to u, set it equal to 0, and after we do that we see that u star becomes, this is minus lambda 2, right. We differentiate, we get the following relation, and then we plug it back to get our optimal Hamiltonian, where u is removed from this equation. So, step 3 is find. So, my optimal Hamiltonian, which is now a function of x 1 star, x 2 star, lambda 1 star, lambda 2 star. So, u is completely out of the picture, and we see that this is also equal to, after plugging in u, is half lambda 2 star square plus lambda 1 star x 2 star minus lambda 2 star square. Okay. After we simplify, I get that this is lambda 1 star x 2 star minus lambda 2 star by 2. Okay. And then I see that so I have to set up my 2n equations or my 2n Hamilton's equation, obtain state and co-state equations. I see the following. So, x 1 dot star is partial h partial lambda 1, and I differentiate, I get that this is x 2 star, and then my x 2 dot star is partial h partial lambda 2. So, that gives me minus lambda 2 star, and then I see that lambda 1 dot star is minus h minus x 1 at star. When we differentiate with respect to x 1, we do not have an x 1 in the expression, I get that this is equal to 0, and lambda 2 dot star is equal to minus h minus x 2 at start condition, and I get equal to minus lambda 1. Okay. So, then so I have 4 equations and I have 4 unknowns x 1, x 2, lambda 1, lambda 2. So, I can slowly start solving. Notice the third equation can be quickly solved. So, I see that lambda 1 star is C3, a constant, because lambda 1 dot is 0, and lambda 2 star dot is minus lambda 1. So, lambda 2 star is the integral of minus lambda 1, will give me minus C3 t plus C4. So, I am just using a set of constants here, and then my x 2 star is minus lambda, x 2 star dot is minus lambda 2. So, then my x 2 star will be integral of minus lambda 2 star, which comes out to be which comes out to be C3 t square minus C4 t plus C2, and finally my x1 star, my x1 star is the integral of x2 from equation number 1 and x2 star, and I see that this is also C3 t cube by 6 minus C4 t square by 2 plus C2 t plus C1, and now I have a set of 4 unknowns C1 to C4, and we also have to see whether we have 4 equations to solve for 4 unknowns. Notice that in this problem we are given the following. Well, I have also specified some boundary conditions. So, my boundary conditions are x bar 0 is 1 2 and my x bar 2 is 1 0. So, essentially I have specified fixed boundary condition. So, these are a set of vector boundary conditions of 2 constraints each. So, essentially we have 4 boundary conditions and we have 4 unknowns, right. So, in order to find this, use our x boundary condition x bar of t 0 and x bar of t f, right, and we will find these constants, right. So, I leave those evaluation of the constants to the students and look at another quick example. So, in the second example I am going to repeat my first example, repeat example 1, but this time with the following boundary condition, with boundary condition as follows. So, I just want to highlight the solution method with the different cases that we have. So, the boundary conditions are x 0 is 1 0 and then x 1 at 2 is 0 and x 2 at 2 is free. So, it is a freely moving state variable. Notice that my initial and the final time are 0 and 2. So, those are fixed. However, my final state x 2 is free. So, this is a case of fixed final time, but free final state. So, this means that we need to use case C in our case C of our simplified boundary condition case. Okay. Let us go back a few slides. Our case 3, our case C is the following: free final state, fixed final time. So, all we need to do is replace one of the condition, the free the fixed boundary condition, with this particular condition, partial s partial x is equal to lambda. Okay. So, what we have done is, so at t equal to t f, I have an condition lambda 2 star at t f is equal to partial s partial x at t f, right. However, it is only the second variable which is free, the second state variable, and hence this is partial s partial x 2, only the second variable is free, right. But also the fact is that s, our cost function, is identically 0, right. So, I get that this constraint is set equal to 0. So, I have my following boundary conditions. So, my boundary conditions are as follows. So, at t equal to 0, I have x of x 1 of 0 is 1, x 2 of 0 is 2 and x 1 of 2 is 0, and finally, my x 2 at so instead of x 2 I replace this boundary condition by my fourth boundary condition is replaced by the fact that lambda 2 at start condition is 0, right. So, these are my 4 conditions to satisfy, and of course, we do the same solution method, we will get an equation, we will get a solution in terms of 4 constants, which are then resolved using these 4 conditions. Let us look at one more example. I am going to repeat my example 1, but with the following boundary conditions. So, again in my third example I repeat I repeat my example 2 with the following boundary condition, x 0 is 1 2. So, this is a vector setup, and x 1 at 2 is equal to 0, x 1 at T f is equal to 3, and x 2 at T f is free. Okay. Notice that I have so notice that my second state variable at final time point is free, and also my final time point T f is also not known. So, we do not know whether it is 2 or whether it is less than 2 or greater than 2, right. So, what we have is, so we have T f is unknown in this problem. So, T f is unknown, and also x 2 at T f is free, right. So, which means that since T f is unknown, T f can very well be a variable to the system. So, in which means that the variation in T f is also non-zero, and the variation in x 2 is also non-zero, which means that we have this situation falls under our simplified case E, where we are able to vary our final time as well as our final state independent of each other, right. So, this falls under case E, and we see that the following set of natural boundary condition must hold. So, I have the following. So, H plus partial S partial T at T f set equal to 0, and well, my S is 0. So, that we will plug later, and second I also have that lambda, the lambda 2, the second state variable. So, lambda 2 is partial S partial x 2 is set equal to 0. This is under starred condition at T f, right. However, my so this is the condition. However, my S is identically 0, the cost function so far, right. So, which means that lambda 2 is 0, and this derivative is also 0, right. So, now I have two conditions coming from, so these two will give me two conditions, right, and I also have two boundary conditions coming at t equal to 0, right, and I have also specified another condition at 2, x 1 at 2. So, I have 5 conditions. So, the question is, do we have 5 unknowns, and the answer is yes, we have x 1, we have x 2, we have lambda 1, and we have lambda 2, and the students can see that the fifth variable is the time point, final time point T f, which is also the unknown of the problem. So, 5 unknowns, 5 conditions, the problem should be fully defined. Okay, then let me finally look at one more example of the same example, but with a different cost function. Okay, so, in my final example, let me repeat. So, I am continuing to repeat my example 1 or example 2 as it is, but with changed performance index. Okay. So, my objective function or performance index is as follows. So, j is 1/2 of x 1 of 2 minus 4 square plus 1/2 of x 2 at 2 minus 2 square plus integral from 0 to 2 u square by 2 dt, right, and my boundary conditions are x 0 is 1 2, the same set of boundary condition, and the state variable at 2, the final time point is free. Okay. So, both the variables are free now. So, which means we have noticed that this is the quantity which is sitting outside the integral is s at T f, right. So, I now have a cost function s at t, which is also equal to half x 1 at t minus 4 square plus half x 2 at t minus 2 square, right. So, these are my cost functions, and what else. So, now again we use the same solution methodology, but now I have a cost function, and notice that we have two boundary conditions here, two boundary conditions, and also I will get two natural boundary conditions from my free boundary, and of course I have 4 variables. So, 4 variables which are my x 1 x 2 and my lambda 1 lambda 2. My final time point 2 is known, and so that should fully determine our system, and this is a system where we have fixed time, but free state, and that is our case C, right. So, this is the case C of simplified boundary conditions. So, I hope, so now, so let me just wrap up this lecture by mentioning, I hope that all the students have been able to get a feeling of how to solve the problems involving optimal controls, and in the next lecture I am going to introduce another method to solve these optimal control problems, namely via the Hamilton-Jacobi-Bellman equation, and we are going to state the optimality criteria, followed by we will look at certain methods of constraint optimization, namely the method of penalty function and slack variables. Thank you for listening. Thank you very much.